Good morning, everyone, and welcome to the Midas Expert webinar. My name is Ruggero Cervellini, and I'm the Technical Director of the C&T Engineering. In this webinar, we will discuss the retrofit analysis of a concrete viaduct. Most of the Italian infrastructures were built in the last century or before, according to load assumptions no more consistent with the actual traffic and seismic demand. But despite our age, they still support a big part of the traffic of our towns. And many of these bridges are often so strictly connected with the net of urban roads that it is impossible replacing them with new ones. For this reason, it is fundamental and sometimes urgent investigating whether the structures can still fulfill their role or if they need to be renewed or restored. All structures were designed according to obsolete rules and codes, where the adjective obsolete does not necessarily mean wrong. The fact we are going to investigate the behavior of the structure 75 years old, nowadays working, implicitly means that it was well designed and built. That's confirmed also by the quality of the calculation and drafts and by the results of non-destructive tests done. So it would be more correct saying that the old codes were incomplete, since they were written taking care of vertical loads, and they did not contemplate the concept of ductility, or if they did, it was only sometimes and implicitly, and neglected the requirements about the post-elastic behavior of structures. What do we expect in analyzing similar structure? We'll probably find good decks and weak pier and foundations with insufficient bending or shear resistance. The viaduct we are going to study overpasses the central train station in Treviso and was built in 1939. It is one of the most important gates of the city because with its 4 ramps it directs the traffic coming from Venice, that is at about 20 kilometers from Treviso. It directs the traffic to the highways, to the ring road and to Treviso downtown itself. These 4 ramps are statically and seismically independent from the viaduct, and for this reason they will not be considered in this webinar. The viaduct is made of concrete and has 3 spans, respectively 24.7, 29.3 and 24.6 meters long. Sidewalks included. The deck is 13.80 meters wide and is skewed with respect to its longitudinal axis with an angle of about 63 degrees. Deck is an orthotropic grid made of 2 main hollow side concrete beams with a variable height from 3 up to 3.80 meters, with a 3rd central beam 75 centimeters tall. The slab is 20 centimeters thick. The deck is not pre-stressed and the transverse secondary beams are arranged at a distance of 17-25 centimeters. Their height varies from 0.74 to 1.14 meters. Deck is continuous with the pier and is simply supported at the abutment with very special cast iron rolling bearings. Bearings are cracked and cylinders couldn't slide anymore on the base plate. The pin was out of the guide and they have been already replaced. Each pier is founded on 9 concrete piles, whose length is not indicated in the original available drafts. According to the usual techniques of construction of the age, the piles are likely to be well bored into the gravel bed located 12 meters below the ground. Anyway, this information is not confirmed by available papers, so for the purpose of the project, it must be considered an unknown. The diameter of the piles is 0.60 meters, and they are arranged at a mutual distance in the pipe cap of 2.40 meters. Piers have a square cross section 1.68 per 1.68 meters, and they are reinforced with 58 vertical bars of 36 millimeters, while stirrups are only 5 bars of 10 millimeters arranged every 25 centimeters along the pier. The preliminary investigations included the geometrical and geological surveys, the material testing to assess the property of the materials, the reinforcement investigation to define the diameter and the position of bars. These investigations were completed by the historical research of the original project and codes and of other relevant facts occurred during the life of the bridge, like earthquakes or bombing in World War II. The results of the preliminary analysis lead to the definition of the knowledge level. That's a parameter defining the cognition of the structure in terms of properties, loading, and behavior. The Italian standards define 3 different levels of knowledge, each one characterized by a confidence factor, increasing the safety factor according to this rule. In the analysis, the confidence factor can be introducing amplifying the partial safety factor for material properties. We can talk of poor knowledge or knowledge level 1 when structural details are unknown and are defined on the basis of a simulated project according to the codes of the era. Material properties too are not known, and the analysis are performed assuming the typical values of the material used at the time of the construction, and only linear elastic analysis are performed. We have an intermediate knowledge level, that is the knowledge level 2, where most of the structural details come from as-built drafts or from limited in situ assessments. The properties of the materials come from original design specification or from in situ tests, and all kinds of analysis are performed. Finally, the third knowledge level is the good knowledge level, and is when complete structural details come from as-built draft or in situ surveys, as well as the property of the materials. All kinds of analysis are performed. The values of the confidence factor are respectively equal to 1.35, 1.20, and 1. The original project of the viaduct contains all the details but the pile's length. The property of the materials were assessed with non-destructive tests, and static and dynamic, linear and nonlinear analysis allowed to assume an intermediate knowledge of the structure with a confidence factor equal to 1.2. The client were concerned about the capacity of the deck to support the actual traffic loads that are greater indeed than the moving load prescribed by the old standards. So the first aim of the numerical analysis is defining the deck and the bearings capacity with regard to the static demand. And the second aim of the analysis is defining piers, abutments, bearing and joints capacity with respect to the seismic demand. The layout of the numerical analysis is load analysis with respect to the actual code, definition of the finite element model, and then the numerical analysis. When the capacity is lower than the demand, the structure needs to be retrofit. And we can choose between two alternative strategies: reinforcing the weak elements, providing the required strength to resist to the design external forces, or improving the structural ductility so that the structure can adapt to seismic displacement and acceleration without relevant damages. The limit of the first approach is that we do not exactly know how large will the real seismic forces be, and the structure could be strongly damaged when the elastic limits of the material are exceeded. On the other hand, there are several well-known strengthening techniques that are easier to apply and often less expensive than the others. In fact, in this case, the ductile approach requires first to separate the deck from the piers, linking them with anti-seismic devices with the required ductility. The ductility of the devices can be calibrated in order to limit the share of piers and abutments at a desired value. The ductility of the seismic isolators can be 10 times or more larger than the structural one. In this case, we propose to use the lead rubber bearings. On the other hand, the intervention is more difficult and expensive, but the final structure can stand earthquakes without relevant damages. Notwithstanding its age, the viaduct appears quite well preserved, with just a few critical points needing to be restored, when the corrosion of the reinforcement caused the breakaway of the concrete cover. Only the sliding bearings of the abutment were seriously damaged. The carbonation is limited within the thickness of the concrete cover, and corrosion didn't affect the reinforcement. As you can see in these photos, concrete is not damaged and only superficial treatments are required. The thick coating of black grease smoke layered by the ancient steam locomotives probably protected the concrete surface from aggressive agents. Concrete assessment required 5 different types of tests. Sclerometric, ultrasonic, and pull-out tests were completed with logging of concrete core samples for carbonation and resistance tests. The position and the diameter of the reinforcement, as well as the thickness of the concrete cover, was assessed with packometer test. The quality of the steel used for the reinforcement was assessed with traction test on sample taken on site. The results of this test permitted to establish, first of all, that the quality of the material is homogeneous in the structure. Then, that the resistant class of concrete is C2530, while steel used for the reinforcement has a yield stress of 315 megapascal and an ultimate stress of 490 megapascal. The geological survey permitted to define the design stratigraphy of soil represented by an alternation of silty sand and silty clay thin layers till to the gravel bed located at about 12 meters below the ground level. The buoyancy is located at 6 meters below ground. The structural capacity with regard to the actual moving loads were defined with linear static analysis, while 3 different analyses were performed in order to assess the dynamic response of the structure. The nonlinear static, or pushover, to investigate the elastic and post-elastic behavior. The linear response spectrum, to evaluate the design forces, to perform the section checks and define the retrofit strategies. And finally, the nonlinear time history for the isolated structure. The nonlinear properties of the materials can be modeled with plastic hinges lumped at the ends of the element, or with fiber models where the section of the element is discretized into fibers which deform axially only. The plastic hinges formulation is computationally more efficient and allows to define the shear capacity of piers too, but a great number of formulations exist for plastic hinges. For the piers of this viaduct, the FEMA 356 plastic hinge was used. In order to check whether the setting of the plastic hinge were reliable with the piers of this viaduct, it was decided to compare the results of a simple benchmark test. 2 models of a single square pier 1.68 per 1.68 meters were analyzed, one with plastic hinges and one with fibers. The pier is 5.25 meters tall and is clamped at the base. The vertical loads are the dead and the permanent load of the deck. According to the Italian standard, the stiffness of the pier is reduced to 50% due to the cracking of concrete. The inelastic properties of the materials are defined according to a bilinear model for steel and to the Nagoya model for concrete. The properties of the plastic hinge for the axial and bending components are auto-calculated by the program on the basis of the reinforcement defined for the concrete design of pier. The FEMA plastic hinge is defined with respect to the moment rotation curve. The results of the benchmark test are represented in these diagrams, where we can see that the plastic hinge offers a good approximation of the bending and elastic behavior of the material, even if the fiber model gives a more detailed description of yield and rupture points. The pushover analysis will demonstrate that the structure will always have an elastic behavior with the maximum displacement at a performance point of about 15 millimeters. And we can see in these diagrams that the maximum error is less than 10%, and for this reason the assumption can be considered suitable with the purposes of the analysis. Now, let me show to you the finite element model. The deck is modeled as a spatial grid composed of 3 longitudinal beams and cross beams. The cross-section of the main beams of the deck are defined with the sectional property calculation tool and then imported into Midas Civil. The sections of the deck are defined with the center top offset, and rigid elastic links connect the different parts of the structures and take in account the actual eccentricities between the center lines of the elements. The pile cap is modeled with plate elements. It's a square plate 6.20 by 6.20 meters, 1.36 meter thick, and piles are arranged at mutual distance equal to 2.40 meters. The verification of the foundation is not required, so a coarse mesh is adequate to pick the dynamic response of the structure with a sufficient precision. Pier section is simply made of square beam column elements 1.68 per 1.68 meters. Even if the pile length is unknown, the foundation must be correctly defined, since the soil-structure interaction has an important role in the response of the structure. Three alternatives were here considered. The first, with piers clamped at mid-plane of the pile caps. The second, with piles clamped at a critical depth ranging from 1.5 up to 3 times the diameter of the pile. And finally, with the piles supposed to be bored in the gravel bed with a length of 15 meters. In this case, the soil structural interaction is modeled according to the linear elastic theory of Winkler modified by Chiaruggi and Maya. The bearing capacity of the foundation is not under discussion here. The structure is not affected by settlements, and permanent loads didn't significantly change during its life. The actual moving loads are greater than the old one, it's true, but their effects in terms of settlement are secondary with respect to the permanent components. For this reason, we can say that the assumption we are doing is relevant only to assess the seismic behavior of the structure. And three different models of the structure will be compared in terms of dynamic behavior with pushover analysis. The nonlinear properties of the material is introduced with the thermoplastic hinge. As always, results are represented in these diagrams for longitudinal and transversal earthquake, where we can see that the clamped pier assumption is too conservative in terms of forces and underestimates the deformation of the structure. The fundamental period is equal to 0.262 seconds. The model with long piles probably gives the best soil structure interaction, but the unknown variable of piles length may lead to unsafe results, because the deformability of soil is relevant with respect to the structural one and may lead to overestimate the fundamental period, that is equal to 0.432 seconds. And more, further expensive geological surveys, more detailed soil analysis should be required to proceed under this assumption. The clamped pile models gives intermediate results and takes into consideration the effect of soil plastic deformation at the top of the piles. It does not overestimate the fundamental period, that is equal to 0.313 seconds. This model is not affected by the limits of a poor knowledge of the soil properties, because their critical depth ranges from 1.5 to 3 times the pile diameter. In other words, a wrong assumption will not particularly affect the results. The clamped pile models will be used for the structural analysis of the viaduct, assuming a critical depth of 1.80 meters. The first question of the client was, can the viaduct still carry the actual traffic conditions? Considering that the structure is not affected by relevant settlements and that the permanent loads did not change until to date, the answer can be found investigating in detail the effects of the moving loads on the deck with a linear static analysis. This picture shows the moving load eccentricities referred to the center line of the deck with the carriage width of 8.90 meters. The eccentricity is equal 2.95 meters on right for lane load 1, or 5 centimeters on left for lane load 2, while the remaining area has an eccentricity of 3 meters on the left. Moving loads per Italian standards are the same prescribed by the Euro codes, and the load combination factors are equal to 1.35 for structural permanent load, 1.50 for non-structural permanent load, 1.35 for moving loads, and 1.50 for the other live loads. The static analysis led to the maximum forces for the ultimate limit states. We can read a maximum positive bending of about 12,000 kilonewton per meters at about at midspan of side spans, and a maximum negative bending of about 18,000 kilonewton per meter in the section at the top of the piers. The ultimate limit check was performed with the Middle General Section Designer tool. Now we can see the verification for the positive moment. The section has a top layer of 25 bars of 36 millimeters and a bottom layer of 18 bars of 36 millimeters. The ratio between the design force and the resistance force is equal to 0.83, and the confidence factor was introduced amplifying the partial safety factor of the material properties, and the coefficient for long-term effects is assumed as 0.85 instead of 1. This is a conservative assumption. The verification is checked for positive moment with a coefficient almost equal to 1, and the same for the section at the top of the pier, where the top layer of reinforcement consists of 25 bars of feed 36, and the bottom layer consists of 7 plus 18 bars of 36 millimeters. The ratio is 0.7, and the section is checked with a coefficient of 0.87. Also the central beam is verified. For the section with positive moment. The reinforcement consists of 220 at the top layer and 330 bars at the bottom layer. The ratio is 0.75 and the final coefficient of the verification is 0.90. The section with negative moment is reinforced at the top with 2 bars of 30 millimeters and at the bottom with 2 bars of 30 millimeters. The coefficient is 0.61 and the final coefficient of the verification is 0.73. The slab verification was performed considering a clamped rectangular area between 2 beams and 2 cross beams. Local direction for sums gives in the center section a bending moment of 12 kN per meter and along the clamped edge a maximum value of 40 kN per meter. The reinforcement consists of a top layer of 1 bar of 16 millimeters every 10 centimeters and of a bottom layer with 1 bar of 10 millimeters every 10 centimeters. The ratio are respectively equal to 0.73 and 0.4 with a final coefficient of 0.88. The slab satisfies also the punching shear verification with a load of 200 kN spread on a rectangular area of 600 per 350 millimeters. So on the basis of these results we can say that the viaduct can still fulfill the actual traffic loads. And now I will explain to you the substitution of the bearings, that starting with the lifting of the deck with hydraulic jacks and the demolition of the concrete base or supporting the old bearings that were removed from their place and substituted with new steel bearings, and the reinforcement exposed during the works were protected against the corrosion with epoxy painting. New bearings are free sliding spherical hinges in which the rotation about any horizontal axis is ensured by the sliding of a convex steel element in a monolithic element covered with SMF, that is special sliding material, a patented special sliding material. The vertical capacity of the bearing is 3,500 kN and permitted moments are plus or minus 50 millimeters for longitudinal displacement and plus or minus 60 millimeters for transversal displacement. In this section we can see where the SMF layer are arranged, and this table compares the admissible contact pressures of the SMF sliding material in comparison with those of the common PTFE, and we can see that they are always the double. This diagram compares the friction coefficient of SMF with PTFE. The different thickness of the devices was compensated with the steel element fixed on a new concrete base. The next step is investigating whether the structure can support the seismic demand. Please consider that in 1939 Treviso and its neighborhoods were not considered seismic areas. They were classified with a low seismicity only in 1972. The actual code defines the seismic reach of each structure not only as an inherent property of the site, but also of the structure itself, depending on its static scheme, loads, ductility and restraining conditions. As I said before, three different kinds of analysis will be performed: the static nonlinear, the linear response spectrum, and the nonlinear time history. The pushover analysis defines the post-elastic behavior of the structure, that is, if, where, and how the elastic limit is exceeded. And the FEMA 356 plastic hinge correctly approximates an elastic behavior of the pier. Two different post-elastic behavior will be investigated: the axial plus bending behavior and the shear behavior. Before approaching the nonlinear static analysis, it's better looking at the modal response of the structure that always gives important information. The first two modes regard respectively the longitudinal and the transversal translations. In the first mode, more than 70% of the masses participate to the longitudinal translation, with a period equal to 0.313 seconds. In the second mode, more than 50% of the masses participate to the transversal translations, with a period equal to 0.293 seconds. And the pushover load can be assumed as proportional to the modal load shape. To the first mode for the longitudinal earthquake, and to the second mode for the transversal earthquake. The master node is at the center of the deck, and the maximum displacement is equal to 10 centimeters. This is the compiled formulation of the plastic hinge, and these are the results. The capacity curve of the piers demonstrate that the performance points is always within the elastic field. That means that the structure can be studied with the linear response spectrum analysis, assuming a structural coefficient Q equal to 1, and the design spectrum shall be the elastic response spectrum. The shear behavior is different because the displacement demand is greater than the displacement capacity, and the structure needs to be retrofit. The design spectra are defined by the Italian code, introducing the geographical coordinates of the structure and some other parameters that define its importance. The class of the structure is the fourth because it is a strategic bridge. The nominal life of the structure is longer than 100 years, and the reference life is obtained multiplying the nominal life for the use coefficient, and is equal to 200 years. The reference life defines the reference return period of the seismic action and the elastic response spectrum. We have already seen the first and the second mode of the structure, and we can say that both periods are within the plateau range. For longitudinal and transversal earthquake, the design forces of pier and foundation are maximum. The ductility verification demonstrates that plastic hinges have sufficient rotation capacity, and the table resumes the verification of the longitudinal and transversal deformation demand for every load or every seismic load combination. The strength verification of piers were performed using the design and check tools of Midas Civil, introducing the confidence factor as a partial factor of the material. As explained before, the coefficient for long-term effects is conservatively assumed equal to 0.85 instead of 1. Looking at the results, we find a similar situation for every pier, and we find that pier almost satisfies the verification for the static moving loads, and they would also for the seismic combination if the confidence factor was equal to 1, or if alpha was equal to 1. With a confidence factor equal to 1.2 and alpha equal to 1.85, they do not bring the maximum coefficient equal to 1.12. As we expected, the bending behavior is not the problem, but sure, pier strength is always insufficient with the minimum coefficient equal to 2.15, and even with the confidence factor and alpha equal to 1, it would be the 1.55, that is too much larger than 1. On the other hand, the results match with what expected, since the seismic risks were not considered in 1939. The viaduct was designed essentially for vertical load, and from this point of view, we can also say that the original assumptions are still valid, but piers now need to be retrofit. It is possible to choose between two alternative approaches: improving the shear distance of pier with concrete jacketing of piers, or wrapping around with fiber reinforced polymers, or reducing the lateral forces. With the pier jacketing, each pier is clad with a concrete jacket 26 cm thick. The dimensions of the section change from 1.68 to 2.2 meters. The vertical reinforcement consists of 32 bars of 12 millimeters along the perimeters, while stirrups are 2 bars of 16 millimeters arranged at 10 centimeters along the pier. These stirrups are completed with 3 plus 3 bars of 12 millimeters through the pier, arranged every 30 centimeters. Jacketed piers are stiffer, and the moment of inertia is almost tripled, and the fundamental period reduces to 0.289 seconds. For these reasons, lateral forces are greater. But on the other hand, the concrete jacket increases the global resistance of the sections. It confines the original concrete core and limits the buckling of the longitudinal reinforcement. This image compares the fundamental periods of longitudinal and transversal modes for retrofitted and non-retrofitted structure. In this table, we can read the design force and the resistance shear. For the non-retrofitted structure, we can see how the design force is always larger in the longitudinal direction. And in this table, we find the same values for the retrofitted pier, and we can see now that the resistance shear is always larger and satisfies the requirements. These diagrams show the longitudinal and transversal design shear force for the retrofit and non-retrofit piers. And these other graphs shows the design shear and the resistance shear for longitudinal and transversal earthquake of the retrofit structure. The carbon fiber reinforced polymer are an excellent retrofitting alternative. CFRP confines the concrete core and at the same time improves the shear resistance without increasing the transversal, without increasing the dimension of the cross-section of the pier. The CFRP have a linear behavior till to rupture, and the graph compares the constitutive diagrams of steel, glass, and carbon fiber reinforced polymers. The rules enforced in Italy for the use of CFRP are the CNR DT 200 of 2004. Istruzioni per la progettazione, l'esecuzione e il controllo di interventi di consolidamento statico mediante l'utilizzo di compositi fibro rinforzati. The shear resistance is assumed equal to the minimum value of the resistance of concrete, of the resistance of steel, and the resistance of fiber reinforced polymer. And the confinement was made wrapping 3 layers of uniaxial fibers with their properties written in this table. And the length of the part to be wrapped is defined according to the theoretical plastic hinge length, that is at about 200.85 meters at the base of the pier. But considering also the plastic hinge at the top of the pier, the full length need to be wrapped. The CFRP retrofit piers fulfill the resistance requirements due to the actual seismic forces. And the most important advantage is that the intervention can be done without interdicting the traffic on the tracks close to the piers. Works are cheaper and will take a shorter time. The diagrams compare the design and the resistance force of retrofit and non-retrofitted piers for longitudinal and transversal earthquake. The second alternative is represented by the seismic isolation, and it is an approach completely different from the first, since it drops the force-based design for the displacement-based design. The inherent ductility of the structure can be increased introducing a concentrated ductility by the means of special devices that decouple the soil motion from the structure motion. The first idea of decoupling the motions dates back to 1870 by Jules Touillon, but it was patented only in 2001 by Ayacuda as the double concave friction pendulum. In this picture we can see the original idea of Touillon and the patented friction pendulum of Ayacuda. The first seismically isolated viaduct of the world was built at about 40 years ago in Italy, and it was the Somplago Viaduct, and it was designed by engineer Renzo Medeotti. It was the only bridge that was not damaged by the Friuli earthquake in 1976. This fact gave a strong impulse to the construction of seismically isolated infrastructures, and in 10 years more than 150,000 square meters of isolated decks were built. The Italian rules for the design of seismically isolated bridges were enforced in 1993 as istruzioni per la progettazione antisismica dei ponti con l'impiego di dispositivi isolatori dissipatori. Today, The reference international standard is the EN 15129 that officially came into force in 2011 after a long process that lasted 18 years. The design aim is limiting the shear force at a pier using devices with adequate ductility. The isolated structure has a larger period, that is, a lower response. The seismic energy is transformed into deformation energy during the iterative cycle of the deformation of the devices. The project considers to isolate the viaduct with lead rubber bearing. The lead rubber bearings are elastomeric bearings with one or more lead core. The lead rubber bearings simply substitute the bearings at the abutment, but in order to locate them between the deck and the pier, it is necessary to cut the structural continuity. This is the constitutive law of a lead rubber bearing, and the design of such a device follows an iterative procedure. The first step is fixing the tryout values of the initial elastic stiffness, of the post-elastic stiffness ratio, of the yield force, and of the ultimate displacement. With this data, it's possible to calculate the effective damping and the scale design spectrum. The calculation of the ultimate so we can calculate the ultimate displacement in the model and compare it with the tryout initial value. If the values differ less than 5%, the iterative procedure can be concluded. The table resumes the calculated values of at the fourth iteration for the lead rubber bearings of this viaduct. The initial stiffness of the rubber bearing of the pier is equal to 15,400 kilonewton per meter with a yield force of 183 kilonewton and a post-yield stiffness ratio equal to 0.13. The equivalent stiffness, that is the second stiffness, is equal to 4,126 kilonewton per meter, and the effective damping is the 27%. For the lead rubber bearing of the abutment, the initial elastic stiffness is equal to 25,000 kilonewton per meter. The yield force is 281 kilonewton. The post-yield stiffness ratio is the 0.053. The linear equivalent stiffness is 4,780 kilonewton per meter, and the effective damping is the 39%. It means that we will see that it means that linear response spectrum analysis are not allowed. Now the tables. In these tables we can read the maximum displacement evaluated at the fourth iteration. We can see that the maximum value is 81 millimeters, that is only 4.80% larger than the target displacement. The lead rubber bearing device can be introduced in the numerical model as a general link with the linear equivalent stiffness value for the linear behavior, and with the parameters for the non-linear behavior, the initial stiffness, the yield strength, and the post-yield stiffness ratio. The same for the lead rubber bearing of the abutments. And the isolated viaduct can be studied with the linear response spectrum when occur the conditions set at the paragraph 7.10.5.2 of the NTC 2008, the Italian standards. The effective damping of the abutment is C equal to the 39%, that is larger than the 30%. For this reason, the linear analysis is not allowed. Nevertheless, it gives important preliminary information about the behavior of the isolated system, and it can sometimes be used to check the reliability of the nonlinear analysis. The design response spectrum is the elastic spectrum scaled with the factor Q only along the components of motion. The fundamental period of the isolated structure is 1.503 seconds instead of 0.313 seconds, and the response spectrum is scaled in the 80% of the fundamental period, that is 1.2 seconds. The red line is the design reduced elastic spectrum. In these tables, we can read the base shear values calculated for the non-isolated and for the isolated structure. Since the linear response spectrum analysis is not allowed, nonlinear time history shall be performed, and the seismic action is described with 7 groups of generated accelerograms. 3 pairs of horizontal plus 3 pairs of vertical ground motion time history components were used, and the accelerograms are consistent with the 5% of the dampened design seismic spectrum, and they were generated with the program SyncWake. These pictures show the time history of the horizontal earthquake and the compatibility with the design spectrum, and for the vertical earthquake, the nonlinear time history and the results in terms of longitudinal and transversal displacements of the lead rubber bearing of the piers. They demonstrate regular behavior and an efficient resetting at the end of the earthquake. Also for the transversal earthquake, the same for the lead rubber bearings of the abutments, and the maximum values of the displacement are grouped in this table, and the diagrams show the results obtained and give the base shear for longitudinal earthquake for the non-isolated structure, for the isolated structure evaluated with linear analysis, and for non-linear analysis. We can see that the linear analysis, even if not allowed, is a little bit more conservative. The same for the transversal base shear. The purple column is the resistance shear, and is always much larger than the design force. Just a note, introducing the isolator requires to separate the piers from the deck, and after the cut, the deck will change the static scheme and will become a continuous beam on bearings. It means that we will have greater positive moments and lower negative moments. So the beams of the deck need to be checked again and maybe retrofitted. The client decided to retrofit the viaduct roping the piers with a carbon fiber reinforcing polymers. These were the reasons of its decision. It is the less expensive intervention. It takes a shortened time and can be done without interdicting the traffic on the track adjacent to the pier. Regarding the seismic isolation of the structure, the client considered that the cost would have exceeded the available budget and it would have had negative effects on traffic over the deck during the construction. We expected this decision, but on the other hand, it was important, in our opinion, calling the attention on more efficient and reliable design approach. That's all. I thank you for your attention, and I will be pleased to answer to any question addressed by email. Thank you and goodbye.